Hey everybody, welcome back. Today we are in Unit 2, Lecture number 4, which we finally get to talk about the least squares regression line, otherwise known as the LSRL, because that's a whole lot shorter than saying least squares regression line. So this is a super important topic in statistics, and it's actually a pretty cool application of pure mathematics just based off of observations and looking at these scatter plots that form a line. Okay, so let's go and get to it and start with our EQ. We want to know, how can we make a mathematical model to make predictions with bivariate data? Well, that's what we're going to work on today. And it is all starting with the regression line. So you need to know that a regression line is simply that. It's a line, but it's going to describe how a response variable y changes as an explanatory variable x changes. That's what a line does, is it tracks motion, it tracks change. As the x variable increases, the y variable is going to either increase or decrease, and if it's a line, it's going to do so by a consistent amount. This is also used to make predictions about a response variable, right? So that's the whole point, or the most valuable part of this, is that we can use this line to make a prediction. When we know the explanatory value, we can predict the response value. And that's the huge part of why these least squares regression lines are so important. Now, the regression equation is y hat equals a plus bx. And that's important to note that this little triangle guy on top is a y that's ready to party. He's got his hat on. We pronounce that as y hat. And that hat is super important. Why is it super important? Because the hat tells you that this is not an actual value that you observed in a response variable. It's a predicted value. It's what the model predicts. It's what is actually on the line, not one of the dots, but it's the actual value of the y variable on the line. So it's what the model predicts for the response variable y at a certain value of the response variable x. Okay? Now, we also know that any equation of a line is going to have two components. You know those components most simply from algebra as y equals mx plus c, where m is the slope and c, or some of you may know it as b is the y-intercept. Stats goes a little crazy though. Again, they're ready to party. I don't know what it is, why we do a plus bx, but this is the way that it's accepted in statistics. So instead of b being our y-intercept, a is now our y-intercept. Okay, so forget about this for a bit and let's focus on this, the y hat equals a plus bx, where a is the value of the y-intercept. It's constant. No matter what value we have for x, it is not going to change. So what does that tell us in context here? Well, it's our predicted value for y when we assume that the explanatory variable x is equal to 0. If we say that x is equal to 0, then we know what the y value is. That's the y-intercept in context. B happens to be the slope. So this is like m that you're used to. It's the rise over run. A positive slope means we're going up and to the right. A negative slope means we're going down and to the right. So this is probably the most important part of your least squares regression line. This is the thing that you're going to have to interpret the most, and it's also the thing that really drives the whole regression line. It's the slope. And here's how we interpret it. For every 1 unit change in x, the response variable y changes by b units. And I have you fill in a lot of stuff here, especially with this one phrase, because you are going to have to be able to interpret this almost assuredly in some written form, or to be able to identify it exactly like this on a multiple choice question on the AP test. Okay? Super important to be able to articulate the slope. Now I know what you might be thinking, well, Mister, I have no idea what's going on, right? Well, let's stop and look at this next paragraph, because this is going to drive our next bit of conversation. Variables like y hat and x need to be defined. Stats is all about context, and we haven't provided you with any kind of context here. Well, let's go ahead and do that. Now, you can define these two things separately, but what we are often going to do is put the names of these variables in place of y hat and x in the regression line. So you're not going to see y hat, you're not going to see x, you're going to see actual words in place of those things. This is preferred because what this means is you are writing the equation in context. Now, let's actually provide some context and take a look at an example while we finish the rest of these notes. So here's our context. You should now see on your screen the scatter plot for these Ford F-150 trucks, miles driven versus value. And what we see here, it's really important to look at what's on each axis. The x-axis has the miles driven on these trucks. That means it's our x value or our explanatory variable. It is being used to explain the change in our response variable, which is on the y-axis, which is the value of the truck in dollars. So think about that for a second. We are using miles driven to explain the change in value or the change in price, and that should make sense. And we also see that this is a fairly strong negative linear relationship, which means we should be able to use one of these LSRLs, and we should be able to use correlation to describe this relationship. We see that it's negative, so that tells me that as more miles go on this truck, the less value a truck is going to have. That should make sense. So let's actually find this regression equation. We use a two-variable statistics calculator similar to what we used in previous lectures, and we find that the regression equation here is y hat equals 38,257 minus 0.1629x. And that doesn't make a lot of sense. I don't know what that means. Let's go ahead and utilize these ideas of context within these definitions. If you remember from that last paragraph, it says variables like y hat and x need to be defined. So let's actually put into the equation, replace the y hat and the x with the variables themselves. So y hat is the predicted value. So the predicted value of a truck is equal to 38,257 minus 0.1629 times the miles driven. Now we at least have some kind of context and we know what we should plug in and where to find certain things. Okay, so let's go ahead and now define each one of these components. Y hat, or the predicted value, or value hat as you see it on the screen now. It's our predicted value, so that's basically just the line. For any given value x, for any number of miles driven, we can utilize the line to find a predicted value of the truck. And that makes sense, value in dollars. A is the y-intercept. If we were to extend this line to where it intersects with the y-axis, we would have the y-intercept. And we can see clearly that that's $38,257, and that's right about where that line meets. What does that tell me? If a truck has 0 miles on it, then its price or value is $38,257. At least that's what our model predicts. So based on the data that we have, we can predict a brand new spanking truck is $38,257. Next, and the most important thing, is the slope. We say the slope for every 1 unit change in x, the response variable y changes in b units. That slope is negative 0.1629. So that's tough to understand what that means, but stop to think for a second. For every 1 unit change in x, for every 1 unit change in miles driven, for every additional mile driven, the value in the truck changes by 0.1629, and it goes down because it's negative. Well, what's 0.1629? It's $0.1629, or it's about 16 cents. So what this tells me, if I try to interpret this in as much context as I can provide, for every additional mile driven on this truck, or on a Ford F-150 truck like these, I predict the value will go down by 16 cents. For every additional mile driven on a truck like this, its price will drop by 16 cents. That's the slope. That's describing the change. And it's super important to be able to articulate that, because the slope itself is one of these things that you're going to have to do it on your LSRL project. You're going to have to interpret it on the AP test, whether it's in a written form or in a multiple choice or both. I guarantee you are going to have to be able to interpret the slope, so make sure you can do it. So that gives us the basics understanding of how to work with these regression equations, and I don't want to take your Algebra 1 understandings about how to work with lines out of this. Please just know all you are for the most part doing is plugging in a value for x and getting a value for y. You just have to be able to interpret those things now. It's an Algebra 1 word problem, just with really gross looking numbers. That's it. So let's start to look at and understand the kind of things you'll be expected to be able to do with these. So To make predictions, you can use the graph by seeing where your prediction would lie on the line. Okay, so let's say I have a truck that's got 80,000 miles on it. If I follow from 80,000 on the x-axis up to where it intersects with that line, and then I go across to the y-axis, I would see that's right around $25,000. That's what I would predict the value would be. If I want to be more precise, I can plug in my x value into the LSRL and solve for the other variable. What's the other variable? Y hat. So if I plug in 80,000 into miles driven into this equation, I will end up with $25,225 approximately. That's making a prediction. Now, I can make two kinds of predictions. The first prediction is what we just did, and that's called interpolation, where we make a prediction using a value within the interval of data, within the interval of the explanatory value, or explanatory variable. We have trucks with miles on it between, looks like about 5,000 miles all the way up to 140,000 miles. 80,000 is within that interval, so it's safe to say that our model is going to be consistent within that. Extrapolation is when we go outside the interval of values. Okay, if we go outside the interval of values, then the linear model may no longer be appropriate. Okay, imagine that we are looking at a truck that has 250,000 miles on it. It's way far out. If I were to plug in 250,000 miles into my least squares regression line equation, my predicted value would be negative $2,468. Now, we didn't do anything wrong here. What that just tells me is that the model predicts that I would owe somebody money if they want to buy my truck. And that doesn't make a lot of sense, right? So I come to you and said, hey, you want to buy my truck? How many miles has it got on it? 250,000. Said, okay, I'll take your truck off your hands, plus you got to give me 2,500 cool ones. It's like, no, that's obviously not going to work. So extrapolation is very dangerous in the land of statistics. So beware of extrapolating too far. At a certain point, your model is most likely not going to be reliable. And that is one of the dangers that we have to be aware of when we are working with any kind of mathematical model like this. So since we use this model to make predictions, one of the natural questions to ask is, well, how accurate are your predictions? If you're interpolating, how close are you actually going to be to guessing the value of the response by just looking at that explanatory variable? Well, that's where these things called residuals come in. They are a way to gauge how accurate our predictions are. Basically, they are the difference between an actual individual's response value and the predicted response value. All it really is the difference between the dot and the line vertically. It's the vertical space between an actual value, an actual individual's y value, and the distance to the line. So it's just that vertical distance from the dot to the line. That's it. Mathematically, we say that is y minus y hat. So you have to have your actual value, and then you find, if we had an identical truck just like this, how much would my model predict it would be? How far off is the actual truck's value versus the imaginary predicted truck's value? That gives you the residual. So, for example, if we examine one of these trucks that has 70,583 miles on it, the actual value of that truck was $21,994. If we were to plug in $70,583 into our regression equation and evaluate it, we would get a predicted value of $26,759. Now, that $26,759, that is the price of an imaginary truck that is identical to this one that is 70,583 miles. Okay? Now let's find the residual. We subtract the actual value, $21,994, minus the predicted value of $26,759. The order of subtraction is very important here. You'll notice that we are going to get a negative value. In fact, it is negative $4,765. Whoop-de-doo, what does that tell me? Well, take a look at the dot and where it is relative to the line. Since the dot is below the line, that tells me that my model, the LSRL, is over-predicting the value of this truck. Now, that might seem like, well, what good is the model then? And if you look at all these other dots, none of these dots are actually on the line. Well, I hate to break it to you, but you're almost never going to have a perfect prediction where one of those dots is actually on the line exactly. The least squares regression line tries to minimize the residuals. That's its purpose. That's what it does. When we plug all of this information into a two variable stats calculator, it looks at tons of possibles of lines that would best match this set of data. And what it's doing is it's looking for what is the smallest value of the residuals. Now, it's fairly complicated what's actually happening here, but by definition, the least squares regression line is the regression line whose sum of squares of the residuals is the smallest, hence least squares regression line. Again, what does that actually mean for you? It means that this line is producing the best line that will have the smallest residual values in total. Basically, the LSRL is in general going to make the closest prediction for your response variable. Or, very simply, it is the best possible line of best fit. And there you have it. That's the least squares regression line in a nutshell. In class, we will go through a bunch of exercises where we'll actually calculate the least squares regression line. We'll plug it all into data. We'll answer a bunch of questions that are going to be very closely related to the stuff that we have just done. Thank you so much for watching. Have a wonderful day, and I will see you next time.